We're starting in on the mnemonic and study material from the one source. So this is just going to be all the additional mnemonics and study material that is on the one source page. So mechanical mixing, we have collective to pitch, which is going to compensate for your rotor downwash on the stabilator. Then we have collective to roll, which compensates for translating tendency. Then we have collective to yaw, which compensates for the torque effect of the aircraft. Then we have yaw to pitch, which is the lift component of the tail rotor being compensated for due to the tail rotor having its own angle that generates lift. Electronic coupling. So in addition to the mechanical mixing, we have collective to airspeed to yaw. So that compensates for the torque effect in addition to the collective to yaw mix, and that's based on the collective position and airspeed via the collective transducer. FCC number 2 commands the yaw trim actuator 100% below 40 knots, and it slowly decreases until you hit 100 knots, at which you will offload all of your aerodynamic force to the cambered tail fin in order to no longer need FCC2 to compensate for the yaw trim. So that's kind of straightforward. AFCS, it enhances the static stability and handling qualities of the helicopter, and it also provides us with autopilot. It has 5 subsystems, and that's going to be your SAS, your trim, your FPS or flight path stabilization, your stabilator, as well as your coupled flight director. FPS is just a very basic autopilot. It enhances static stability through long-term rate dampening in pitch, roll, and yaw. Generally, people will say that the FPS is the brain of the system. When it's coupled with trim and FPS, it has 100% control authority. Then importantly, when you're below 50 knots, you're going to be looking at attitude hold pitch, attitude hold roll, heading hold yaw, and then above 50 knots, you'll get a little bit more. You'll get attitude hold and airspeed hold pitch, attitude hold roll, and heading hold and turn coordination for yaw. These systems must be on and operational for FPS to function at 100%, so you need SAS1 and or SAS2 enabled, SAS boost enabled, trim enabled, as well as the stabilator. And it says that it's not required, but in order to be able to readily make changes, the stabilator being in full auto is kind of important. Trim provides a gradient and detent holding force for pitch, roll, collective, and yaw. It consists of 3 electromechanical actuators, collective, roll, and yaw, plus 1 electro-hydromechanical actuator, which is your pitch. SAS boost is required for trim to operate. Without that, it functions as SAS off, where you'll have all that sloppiness in the controls and free movement. Slip clutches require 80 pounds of max force in the yaw axis in order to control them. 13 pounds max in the roll axis, and 22 pounds max force during an actuator jam. The FCC monitors continuously and will turn off driving the trim actuator if there is an issue. SAS 1 and 2 provides short-term rate dampening in pitch, roll, and yaw axis. It enhances turn coordination above 50 knots. It provides hover augmentation under 50 knots, and it has 5% control authority for each SAS module. It is also controlled by the respective computer, or FCC, for your number 1 and number 2. Input, you have pitch, roll, and yaw signals that will come off of your respective EGIs, and then you have airspeed data, which will be collected by the air data computer. Malfunction is indicated by erratic movement. And if you do have a malfunction, you're just going to reset computer 1 or computer 2, or both, and then turn off that SAS if you're unable to reclaim the system. It's kind of amazing what a computer reset will do in terms of regaining control. AVCS, so that reduces cockpit and cabin vibrations by mechanically generating additional vibrations that are out of phase with the main rotor, and that's between 90 to 105 NR. And it uses 3 force generators that are spread out across the aircraft in order to create that opposite phase vibration that cancels out the vibration. Stabulator, variable angle of incidence airfoil that enhances handling qualities in the pitch axis in forward flight. And stabulator is where we're starting to get into the mnemonics that are associated with the aircraft. So scalp is the mnemonic that we're going to be utilizing, and your scalp is streamlines, collective coupling, angle of incidence, lateral side slip to pitch coupling, and pitch rate feedback. And we'll go into each one of those right now. So it streamlines the stabulator with rotor downwash at low speeds below 30 knots in order to have a minimum nose up attitude, which will be caused from the downwash, and that's fed by the ADC and FCC. Collective coupling, so to minimize pitch altitude excursions or porpoising due to collective inputs, the collective position transducers will put out a signal that will couple and ensure that you're not porpoising. It begins at 30 knots. Angle of incidence decreases above 30 knots for improved static stability. Lateral side slip to pitch coupling. So in order to reduce gust susceptibility, the stabulator will go up for right pedal and stabulator will go down for left pedal in order to utilize its lateral accelerometers and keep a steady side slip. Pitch rate feedback to improve dynamic stability. It dampens pitch excursions due to turbulence or g-forces, so that's powered by the EGIs and FCCs. That's about it for the stabulator. We're going to go into fuel flow. So fuel flow in the engine, the acronym that I like for it is PF low. So that's, just remember, PF Chang's some people think it's high tier, but it's actually low. So PFHLO, and that's pump, fuel filter, HMU, liquid to liquid cooler, and ODV, and that's the general fuel flow of how everything goes through the system. And then the ODV itself, we have another mnemonic that we're going to use for that, and that's HOPS. So HOPS is hot start prevention, overspeed protection, purge, and send fuel. So hot start prevention shuts the fuel flow down at 900 degrees Celsius, NG less than 60%, NP less than 50%. Overspeed protection, NP from the DEC at 120 plus or minus 1. You'll have overspeed protection kick in. It'll cut out the fuel flow in order to allow the system to drop back down and not over NP. And you'll probably already seen that in the simulator at this point if you're studying this. Purges main fuel manifold and allows backflow of high pressure air for purging, which also assists with ensuring that you don't have coking. And then it sends fuel through the manifold to 12 injectors for starting, acceleration, and engine operations. Then we have the HMU. So HMU provides basic fuel control, including high pressure fuel pump and variable geometry servo actuator. The acronym or mnemonic that we utilize for this is PM can veto. I prefer the veto version just because you either have a EDECU or a DEC. It doesn't really matter which one, and the mnemonic works a little better with PM can veto. So that's because it pumps, meters, collective to pitch compensation through the LDS, acceleration, deceleration, NG limiting, variable geometry positioning of the inlet guide vanes for optimum performance, EDECU lockout and pass override, torque motor to trim NG output, and opens the vapor vent. So that's our PM can veto, and that's pumps fuel at high pressure, meters fuel to the ODV in response to the power available spindle, load demand spindle, utilizes the torque motor from the DEC and engine variables in order to make that metering happen. Collective pitch compensation through the LDS spindle. When the collective is moved, the NG is reset for immediate NP response. Acceleration and deceleration flow limiting, preventing compressor stalls, engine damage, or flame out. NG limiting limits max torque available under low temp conditions. Variable geometry positioning of the inlet guide vanes for optimum performance, which I accidentally said earlier. EDECU or DEC lockout, power available spindle override and control with the DEC or EDCU inoperative. It allows the pilot to mechanically bypass the torque motor inputs. So I think we're all familiar with lockout. Torque motor to trim an NG output, or to trim NG output. To fine tune engine output, it can be overridden into DEC lockout. and then opens the vapor vent for manual HMU priming and to remove air from the HMU. And that's basically to ensure your fuel flow is consistent. All right, so then we have the DEC. So that controls the electrical function of the engine and transmits the operational info to the cockpit. The mnemonic that we're utilizing for this is in flight HOT, which is INFLT HHOT. It's isochronous NP governing, NP reference, fault indication, load sharing torque matching, transient droop compensation, history counter, hot start preventer, overspeed protection, and TGT limiting. So that isochronous NP governing, that's your DEC will maintain NP reference. That's your inker-dinker switch in your cockpit. So once you have your NP reference set, the DEC will maintain the reference that you have set. NP reference from a cockpit, so inker-dinker switch for between 96 and 100 is what is the settable allowable limit for that. And then fault indication, the DEC code sent to the corresponding engine torque indication in the FMS DEC status page. So that's where you'll have your either 1.5 or 2.5 in your torque indication, indicating what type of fault you have. There's also the additional page inside the materials that goes over all of the other faults that are possible to have the DEC show up with. Load sharing, torque matching, increases the torque of low side to match up to 3% NP above reference. Transient droop compensation, 4-to-1 improvement to compensate for transient rotor droop, uses collective position transducer signal in order to be able to tell how much power it needs to compensate. History counter sends signals to the history counter. Probably seen that on the side of the engine already. Hot start preventer tells ODV to shut off the fuel when 900 degrees Celsius is reached. NG is under 60, NP is under 50. Overspeed protection triggered when NP reaches 120 plus minus 1. TGT limiting limits fuel flow when reaching approximately 879 for dual engine or 903 for a single engine when opposite torque is under 50%. The easy way to remember this, and it's actually really important, is these are the temperatures that are going to be the end point of your final ranges. So you got your 903 to 949 and your 879 to 903. So keep those in mind for dual engine and single engine. Engine alternator. We have 3 windings for 3 functions. So NG signal actually comes from the engine alternator. It's the green cable that's attached. We also have the ignition power that is going to be your yellow cable, and that's for the ignition exciter into the actual engine itself. And then we have the EDEC-U and DEC power cable, which is also yellow. Loss of alternator does not result in a high side failure. We then have our weight on wheels switch, and the mnemonic for this is chaff aim tube. That's CHAFF AIM TUBE, and that's your CVR, FDR, IBIT, erase on ground, hydraulic leak test disabled in flight, audio for low NR disabled on the ground, flight director modes enabled in flight, FMS model aircraft, EGI GC or GPS alignment IBIT on ground, EGI air alignment in flight, AFCS pitch, roll, attitude, hold, heading hold, maneuvering stabilator, radar altimeter hold, airspeed hold enabled in flight. So once you get off, you actually have all of the AFCS activities enabled. IFF mode 4 zero eyes enabled in flight. MFD status page activation on the ground. Thermal protection for the backup pump is enabled on ground. Under frequency protection is disabled in flight. Backup pump will come on in flight automatically if needed, regardless of switch position. Feature is disabled on the ground unless the accumulator is low. And then you have your ESSS jettison, which is disabled on ground. All right. Additionally, and this is the last one here, we have our equipment that is available with battery power only. So The pseudo mnemonic that I came up with this is FAD ICE as farm GIFs BVV CCCH, and GIFs is JIFFFSS. So I broke it down into subsections to try and make it somewhat memorizable, as it was literally just a incredibly daunting list, and it still is. You have your number 1 FM radio, your number 2 error data concentrator, your number 2 DCU, your ICS, CVR and FDR, number 2 EGI, APU system control, stave actuator for your number 1, fire detector and extinguisher, audible warning system, radar altitude, pilot inboard MFD, your jettison, IFF, pilot FMS, pilot FDDCP, fuel transfer, searchlight, SAS control. Then you have your backup pump control, VOR and ILS, VHF, compass light, cockpit utility light, clock, hook, release. Well, clock and hook release. So that's one way to attempt to memorize that. It's a pretty daunting list, but if you just think about what systems you lose, it's relatively easy to come up with what systems you have remaining.